Thank you. It's my pleasure, to get this talk and to talk about, our effort on the microplastic. So, uh, sorry, I missed the first half an hour because I was giving another talk in another room, but I assume everybody very aware of microplastic, and that's why we are here. Okay, but uh, I have been working with a federal agency called NOAA. Okay, so they have a little bit different definition. They are care about the marine debris. So those are pretty, a bigger, plastic junk, in the ocean. But when you come to the size, less than 5 millimeter, so we'll define as a microplastic. And I'm sure, already everybody aware of it is everywhere. Okay, so uh, we were really fortunate, to funded by NOAA and uh, the USGS, try to come out something like how can we monitor, and capture, removal of this microplastic by holistic approach. Okay, I know this sounds really broad, but basically, if you look at the, currently, how we monitor microplastics, so you really labor intensive, right? You have the people go to the field. So here is using the fishing nets, just collect a plastic on the surface water, and then you come back, bring them back to the lab, and then a lot of times just the you know tell by the visual. Okay, although there's actually a lot of demand, you have to report the chemical information either using the FTIR or Raman, but still, because the traditional sampling suggestion, right? So you have to, it's very labor intensive in the when measure. So USGS is a federal agency. They basically just want to provide the scientific data. They are not really take anything for politics, but they are. So when we working with them, how can we build those kind of like microplastic sensor, which allow us to deploy it on the field, and then we can monitor it, in the long term. So this is a challenge, we all face it, right? Because currently, NOAA established a product called the NCEI website. So on this website, you can look at the historical data about the microplastic, anything from the paper, from the literature. But if you look at the map, okay, this map has a lot of dots. Okay, those are the dots are reported the microplastic data. Okay, and but you see that in the United States alone, you got nothing because we haven't really paid attention to those kind of like the things, and also another challenge is this is a really labor intensive process. Okay, so how can we understand how this how much microplastics concentration, and more important, what's their transport, and eventually how the plastic will go. So those are still open questions, for the field. So we build a system. Okay, and this system basically have the two components. The first thing is the by the computer vision. So we have the high speed camera, for the the visual of the plastic material. And another key component is Raman spectroscopy. Okay, so I assume everybody know the Raman spectroscopy, but the idea is different plastic, they basically give you a different signature, and then you can using this signature to as a one source information to tell their chemical type. Okay, so this is what we want to do. We want to couple the 40 devices. Okay, so for these 40 devices, we basically pump the sample from the surface water. Of course, there are several filtration separation devices, but in the end, can we put just in front of the Raman, okay, and that is fully through, okay, and usually the when you're doing the Raman, right, each microplastic will take a couple, maybe 10 seconds to get enough signal to be able to visualize. But since our goal is try to do those kind of inline high throughput detection, we basically have the flow, control in a way they're flowing just on the surface of the glass channel, and this Raman signal you collect basically, will inverse proportion to the flow rate, okay? Because the higher flow rate you are pushing the microplastic, the last time you've got a Raman exposure and the last signal. So you can either stop the flow and get a really high signal to noise ratio of the Raman, and then using that for chemical identification, or you want to improve the flow rate, you just punch it, okay? But now you really got in those kind of noisy data, okay? So in the traditional analytical chemistry, you definitely want to, can we just enhance the signal a little bit, right? Just get a slow flow. But I'm electrical engineer, so I like to see what is kind of like a machine learning and other thing can we push the boundary here. So my student actually come out those kind of like a framework. Okay, so basically, we have the all. So one of the challenges for microplastic, they are probably like if not a million, definitely hundreds of thousands of different plastic. Okay, we start with a very simple 50 different very common plastic type, and then we basically build the library on this Raman signature, and the student will have the so those are the data you collect on the field, and those are the you reference to the library, and then using kind of like a algorithm, you can tell the the type. Okay, so this is kind of like a result you show. Okay, so usually when you have the Raman signal, okay, you pretty much require the signal to noise ratio at least a 3 to 5. Okay, let's face it. Okay, but now if we really reduce the exposure time in order to push that for the throughput, those kind of like are pretty noisy data, and the algorithm basically will try to look at those kind of like a significant peak and look at the reference document, and then you can using that information to for the identification. Okay, but there's some weakness over here, I must say. Okay, because a lot of the Raman structure, you are not just look at the peak location, you are also look at their shape, because their shape means something like a LDPE or HDPE. They are the same plastic, but because they are different density, the Raman will give you some different the peak, and those are really the one of the future work we try to overcome. Okay, but in the end, those are the some kind of like a data. He's try to get the between the trade-off. Okay, so and it pretty much just showing here the precision what you can get from the control sample pretty much really align what you already know. Okay, of course how can you expand those kind of knowledge to the environment, which a lot of things you don't know. That's another other challenge we need to overcome. But nevertheless, we actually have working with the NOAA has those kind of like marine debris challenge grant, and we actually really want the international collaborator to get some kind of like on web on Zoom presentation altogether, and because this is the problem you cannot solve just by our own group, but also the internationally. Okay, so so this is actually the funding right now. We are funded by NOAA and USGS, and thank you so much.